naming and drawing cyclic hydrocarbons. So these are hydrocarbons. These are not considered the aromatics. These are still aliphatics, and these are cyclic. So they pretty much form circular carbon chains that pretty much kind of link up into a ring formation. So hydrocarbon ring structures are called cyclic hydrocarbons. They occur when the two ends of a hydrocarbon chain join together. So we take the outer parts of the hydrocarbon, right, and we bond them together. Right? So we take the two outer carbons, we remove the two hydrogens, and we link it together in the following chain. So here's an example of a hexane hydrocarbon, C6H14. We're going to remove these two hydrogens to allow for that valence electron here on either end to bond together with one another to form this circular ring. So what we have here is pretty much a linear, right? and we're going to use linear / condensed method of drawing these hydrocarbons just to make things simpler. So we're not going to really be drawing, I'm not going to be asking, at least my class, to worry too much about drawing them in this format. I'm going to be asking you actually to draw it more linear. Now this plus two hydrogens just shows that these are the two hydrogens that need to be removed in order to create this ring formation between the carbons. Okay. Now, thing to note, the general formation of cycloalkanes is CnH2n, right? So notice that this general formula is exactly the same as the alkenes, right? The ones with double bonds, but they're not alkenes. You may have a cyclic alkene, you may have a cyclic alkyne, right? So, and we may see that, right? But it's got a similar pattern to the alkenes in terms of the CnH2n. Now, because of the ring structure, the naming rules for cyclic hydrocarbons, which include both cycloalkanes and cycloalkenes, are slightly different from those for alkanes and alkenes. Okay. Now, a few of the rules that we're going to see. So I'm going to show you a couple of examples. I'm going to show you just how important, what kind of rules are going to come into play when dealing with these cyclic hydrocarbons. Now, if we have a single carbon-carbon bond as such, right? So what we have is, remember as we said, at each vertex of a line, there is a carbon. So we know it's an arrangement of a pentane, right? But it's a cyclic pentane. Now, we've got 5 corners, 5 atoms in the ring, which is the main chain. Now, notice that there are no branches, so the name of this compound is just a cyclopentane, right? So what we're going to be doing is we're adding the word cyclo in front of the number of carbons in that chain. So there are 5 carbons, right? So it's a pentane group, but it's a cyclopentane. Okay, notice how there are no double bonds, there are no other branches on this chain. Notice that the addition of the cyclo, as we said, to any ring structure. So make sure, and if you see it in the name, the word cyclo, you know it's in a ring formation, right? If you see a ring formation, make sure in your naming part you include the word cyclo. Okay. Now, when naming cyclic compounds, all carbon atoms in the ring are treated as equal, right? So any carbon could be the number 1 carbon. Now, this means that any carbon, as I said, can be the number 1 carbon. Now, only one branch is attached to this ring, therefore the carbon that the branch is attached to has to be the number 1 carbon. So because we've got a branch in this cyclic hydrocarbon, we must label that carbon as the carbon number 1. So that's the only rule. If we didn't have this, any one of these corners could be number 1. But because we do have, right, because we do have this branch chain, that must be the number 1 carbon. Now, because this branch automatically gets the lowest possible position number, right, because the lowest one is a 1, right, we do not need to show a position number. So we can actually name this a methyl cyclo, right, circular hexane, because there are 1, 2, 3, 4, 5, 6 carbons in this ring, right? So we've got 6 carbons, it's cyclic in nature, and it's got a methyl group located on the number 1 carbon. We may write it down as a 1-methyl cyclohexane, but because we know that it's got to be on the first carbon, we do not need to write in the number 1. Now, when 2 or more branches are on the ring structure, each must have the lowest possible position number, right? So we can number this any which way, right? So let's give this one, let's say, a number 1, number 2, number 3. Right? I could give this number 1, this number 2, number 3, number 4. This would become number 5. So what we want is we want to number it in a way where all the chains will have the lowest possible number. Okay. Now, for the following example, it's best that the ethyl branch is considered carbon number 1. So ignore the way I numbered it. Right? We started up here. But because the ethyl group we want to consider it first. So we're going to number this as the number 1 carbon. So we have to pick now, from after we've identified our number 1 carbon, we have to figure out, are we going to go clockwise or counterclockwise in counting the next carbon. We always want to count it in the direction where, well, we've got 1, 2, 3, 4. This becomes the number 5 carbon where the methyl group is. But if we count it the other way, this is 1, this is 2, this methyl group is now on the 3 carbon. So we want to number it in counterclockwise motion. Okay. So, therefore, name of this structure, right? We've got in this chain, right? We've got, it's a hexane group. It's circular, so it's a cyclohexane, right? We've got a 1 ethyl group. Right? We've got an ethyl group on the number 1 carbon, and we've got a methyl group, right, on the number 3 carbon. So the name of this structure is a 1-ethyl, 3-methyl cyclohexane. So notice how no hyphens, no commas between the methyl cyclohexane, because it's all letters. Remember, we put hyphens in between numbers and letters, or letters and numbers. But with the whole thing, we write it down as one complete word. So now, double bonds get priority for the lowest number. Okay, so normally we would number this as number 1. But because we've got a double bond in our chain, we are going to number it first, right? Which means that even our branch group has to have the lowest possible number. So here's the double bond. I can number this as 1, but number 2 is not going to be here. Number 2 has to be the other end of the double bond. So which means this would be number 3, this would be number 4, 5, and that would be 6. But look at that now. If we number it that way, we're going to get a 6 for our methyl group, right? So it's way too far. So let's try it out, numbering it the other way. We are going to number this as the number 1 carbon. We're going to number this as number 2, right? Because the 1 and 2 have to be between the double bond, which will make that the number 3 carbon. So we know we've got a hexane group, but because it's a double bond, it's got to be a hexene group, right? It's a hexene group, but it's cyclical in nature. It's a ring structure, so we put cyclo, so it's a cyclohexene, right? Where is that located? It's located on the number 1 carbon, right? And we've got now a methyl group. Where's the methyl group? The methyl group is on the 3 carbon, right? So the number 1 carbon has to be on one of the ends of the double bond. Now, then decide which direction to count so that the branch gets the lowest possible position number, which is what we just did, the number 3 carbon. Then you can count clockwise so that the methyl group on the top carbon of the ring has the position of the number 3 carbon. Now, counting in the other direction, as we said, would have given us the branch being on the number 6 carbon, and we don't want that. Okay. So, what is the name of this? It's a 3-methyl 1-cyclohexene. And notice the ENE, because there is a double bond. Where is that double bond located? It's located on the number 1 carbon in the ring. We've got a methyl group located on the number 3 carbon of this ring. Okay. So let's look at a couple of sample problems. Name the following compound. So first things first. Right? Remember how we said we always name things based on the longest possible chain. We are going to name this based on the ring. So this ring is a 5-carbon chain. So we know it's part of a pentane group, but because it's cyclical in nature, it's a ring structure, it's a cyclopentane. Now, we have to figure out what are we going to number these carbons, right? So remember that when we are numbering the carbons, we are going to number it from the, from any one of these carbons, right? So we're going to want to number this based on the biggest chain. So we've got this carbon here, okay, this ethyl group, which will be the number 1 carbon, the number 2 carbon, and the number 3 carbon. Okay, so we know that on the 1 carbon, we've got a 1-ethyl group. On the 3 carbon, we've got our methyl, and it's a methyl cyclopentane. Now, let's look at the next sample problem. Name the following compound. So take a moment. Now notice how we've got branch groups, right? Part of the chain, or the ring hydrocarbon. We also have a double bond located. Right? So remember what the rule states for double bonds in the structure. So take a moment, work this one out, and see if you get the same answer. Now, as we said, the double bond must take precedence. So, we have the option of numbering it here 1, which means this must be 2, or this can be carbon number 1, and this could be carbon number 2. And we got to number it in a way where these branched groups will have the lowest possible number. Right? So if we number it like this bottom one, this is 1, 2, 3, 4, 5 carbon. Right? 5th carbon is the highest number of carbon that our last branch will be a part of. If we number it the other way, I'm going to use the green. 1, 2, 3. This would be 4, 5, and that would be 6. So this way, if we numbered it this way, our one of our ethyl branches will have a number, will be on the 6th carbon, and we always want it based on the lowest carbon. So we're going to use the numbering as I did in red. Now, let's look at the chain. When we're naming it, we're basing it from our ring structure. So it's six sides, so 6 carbons, so we know it's some kind of a hexane. But because of the double bond, it's a hexene. Because it's a ring structure, hexene, it's a cyclohexene. Where is the ene, right, the double bond, located in this? So we numbered it with the green as the number 1 carbon. So it's a 1-cyclohexene. We've got 2 ethyls, right, 2 carbons. So monkeys eat. So 2 so ethyl group. So we've got a diethyl branch. Where are they located? They are located on, not in the green. We're using the red. Ignore what I said about the green. We're using the red, and it still doesn't change. It's still on the 1 carbon. We're using the red way of labeling for the carbons. So we are going to label this, the diethyls on the 3 and on the 5 hyphen diethyl group. So the name of the following hydrocarbon is a 3,5 diethyl 1 cyclohexene. Okay, so ignore the way when I said refer to the green. We're referring to the red, right? So we've got on the 1 carbon, we've got our double bond, 6 carbons in a ring structure. On the 3 and 5 carbon of that ring structure, we have 2 ethyl groups located on them. So remember, when we're numbering them, we are numbering them in accordance to, right, the lowest possible number for our double bond, and these side chains here must also have the lowest possible number as well. Next sample problem. Draw a condensed structural diagram for the compound 1,3-diethyl 2-methyl cyclopentane. So now, be really careful. Now it's a condensed diagram, right? So we still want to show, but the condensed part, what I do accept, it will be these branched side chains, right? So the ring is okay if you draw it as a linear, right, as a line structure, right? Just the straight lines. But the branches, you must show the carbons, right? The carbon bonds, and then how many hydrogens are associated with each one of those carbons. So take a moment, try drawing this one out, right? Use the rules, and see if you get the same answer as I do. Now, when we're drawing such a diagram, we know it's cyclo, so it's going to be in a ring shape. Pentane, right? No double bonds. So we're going to draw 5 carbons in a ring pattern. 1, 2, 3, 4, 5. Now, because this is a pentane, there are no double bonds, which means I can number this ring in any direction I want. But as long as I pick what my numbers are going to be, I stick to going either clockwise or counterclockwise. It doesn't matter. Like I said, because it's a single bond chain, or a single bond ring, sorry, we can number any side. Right? Now, we use the numbers, the 1,3-diethyl, 2-methyl. So it doesn't really matter which one you want to draw first. I'm going to do the methyl group. So on the number 2 carbon, I'm going to draw a 1 carbon methyl group, and that 1 carbon has room for 3 hydrogens. Now on the 1 and on the 3, I'm going to draw my ethyl group, and an ethyl group has 2 carbons. Right? So now, the first carbon has 2 bonds, so we have room for 2 hydrogens on both sides. The last carbon on the outside is bonded once, it has room for 3 hydrogens. And that's it. And that's all you're going to need to label. So notice now, the real condensed part when I'm drawing are my branches. But my ring, we just use a regular line structure. Right? And as I said before in previous videos, whenever you're drawing, double check from your drawing. See if you can get the original question based on your answer. So if you got time on a test or a quiz or the exam, right, do your double check. Go backwards. Look at your drawing and say, okay, here are my branches. Here's my ring. Do I get the same name as I'm given in my question? Next sample problem. This will be the last sample problem. Draw a condensed structural diagram for the compound 3-propyl 1-cyclobutene. So take a moment, work this one out, see if you are going to get the same answer. Now, first things first, we always want to deal with our main chain. So, cyclobutene. So it's a derivative of butane, right? So if we think of our Greek prefixes, none of the Greek prefixes come to mind, which means the rule, monkeys eat peeled bananas, should come into play. So the word bananas is on the 4th, so which means this has a 4-carbon ring. So because it's a 4-carbon ring, right, we've got a square. 4 carbons, each corner represents the carbon. So we've got the 4 carbons, we've got an ene, right, which is derivative of butane, but because we've got an ene ending, it means we've got a double bond. Where is the double bond located? Our double bond is located on the number 1 carbon. So we can number this any which way we want. So I'm going to number it 1, 2, 3, 4. But now, I've numbered it any way I want. I can still do that. Now, it's important that I put my double bond at the right spot. So my double bond will be right there. There's my double bond. Now, I got to show a propyl group on the number 3 carbon. Monkeys eat peeled. So 3 carbons. 1, 2, 3 carbons. This first carbon, 2 bonds, 2 hydrogens. Second carbon, also 2 bonds, 2 more hydrogens. This last one has only 1 bond, only room for 3 hydrogens. So here is my drawing. This is a 3 propyl, 1 cyclobutene. Okay, so they're not very hard. My advice to you is practice, 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 right? Go through online, you can find a whole bunch, just kind of type in and do a Google search for, cyclic hydrocarbons, practice your alkanes, your alkynes, alkenes, practice, 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 practice drawing them, and that's really how you're going to really master the basics of naming hydrocarbons, because ultimately where it's going to lead to is what's going to happen when we start to include things like chlorine into the mix, right? If we're going to add some of these halogens, right? And so as we move on into the even higher levels of naming hydrocarbons, we're going to be introduced to other functional groups that will pretty much bond to some of these carbons. So these are the simple hydrocarbons, and I hope these videos have helped you master your ability to name and draw these simple aliphatic hydrocarbons.